So we have this J, oops, it's not quite right. It's basically integrating over the surface. We have the impressed current dot ds. I just skip the argument here, plus the conduction current dot with ds plus d dt integral over the surface, the electric flux density dot ds. So these are the two main relations that we apply for chapter 6 and chapter 7, right? So the key thing is basically this particular right here, the term with time varying part. So that's what's the difference from previous chapters. So I think the beginning of chapter 6, we talk about how to use this to determine, and then we give this a name called the EMF, right? The induced EMF, electromotive force. So this is basically the idea that if I change the flux, and I will generate some kind of voltage across a loop, or if I change the whole thing. So this whole thing, we call it the total flux, that cutting across through area. So that's the, if you look at the example in chapter 6, that has something to do with the transformer or generator, right? For transformer, only this term changes. This term doesn't change. But for transformer, this may or may not change, but this is changing, all right? And then we learn about the later part of chapter 6 is this term, which if you look at this carefully, this is nothing but the so-called impressed current. This is the current that we put in on purpose. This is the current resulting due to conductivity in the medium. So that is the so-called conduction current. And this term corresponds to what we call the displacement current, all right? So this, of course, you can sum them up together because they are all current. So this term is interpreted as displacement current. Now this current exists if the field exists. In other words, D is related to the E. So in the medium, if the conductivity is approaching infinity, or if you're a perfect conductor, then this term is 0. Therefore, you don't have displacement current. So for any other medium where the conductivity is not perfect conductor, the conductivity is not infinity, then you will have some displacement current, some conduction current. This is the one that you put in. So for so something that you impress, right? So this is called the induced magnetic field. Okay. So in chapter 6, we probably make use of the integral form. And then in chapter 7, basically we look at the special solutions, namely where the field is plane wave. So toward the end of chapter 6, they talk about how to convert this into time harmonic. So then you have the corresponding, yes, questions? Yeah, I thought you have a question. Anyway, so this is the integral form. And then the differential form is basically curl of E. I put a script here, equal to minus partial derivative with respect to time, the B, right? And of course, we are assuming that for this particular form to be correct, what do we assume? We assume that the system is stationary. The surface doesn't change, right? So this can be used for the transformer kind of problem, for typical electromagnetic wave propagation problem that we saw in chapter 8 and chapter 7, where the structure is stationary, right? If it's not stationary, you have to account for these changes, okay? So this can somehow mess thing up. Okay, so now the corresponding term for this one is, the second one is curl of H equal to basically impressed current density plus the conduction current density plus partial derivative. Now this, again, we assume that the system is stationary, right, of D. Now I do not put the dependency now. So this term is nothing but sigma E, right? This is, let me write down, this is nothing but sigma E. This is sigma times E. All right, so this is general time variation. So this is basically the focus of 6, 7, and 8, and so on. And actually after chapter 6, these are the equation that we are working with. And the key thing in chapter 6, 7, 8, and so on is the application of this. But then we look at special situation where, all right, if I put my, I have some kind of fluxes that's changing, like for example here, what kind of voltage that will be induced. So we apply that for transformer problem, for example, or for sensing problem, for example, in your very first lab, you have a clamp ammeter, right? You have an ampere meter to measure the AC current. Now the AC current on the wire produces magnetic field, and it changes with time because you know AC current changes with time. And then what you do is you clamp that the ammeter so that all the field is captured in that core of the ammeter, and then the ammeter then will measure. They basically produces this is what you read, right? So this is how for transformer, one end of the transformer you provide current here, and you generate magnetic field, and on the other hand produce another electromagnetic force on the secondary windings. And the other problem on chapter 6 is, well, if you are given a structure like a capacitor circuit, what kind of current flowing through? So if the material in the capacitor is have some conductivity, the total current will be including these two terms, right? And then in chapter 7, we simply look at a very special case of the solution of this combined. So from here, then we get into the time harmonic case, right? The time harmonic case, what do we have for time harmonic case? Let me use a different color. So time harmonic case, so for time harmonic, then what we have is basically, this is no longer function of time, so I use the block E, which is function of space only, equal to minus partial derivative of the time. Block, this is only function of space, right? Oh, sorry, there's no partial derivative of time anymore. It is basically, what do we have in this case? If it's time harmonic, this minus J omega mu H, right? Function of space only. And then similarly, we have curl of H, which is function of space only, equal to, of course, we have sigma times E, function of space only. If it's a source-free, time harmonic and source-free, then I don't have to worry about the impressed current. Then I have this plus J omega epsilon E, right? Function of space only. Any questions? So the key thing toward the end of chapter 6, at the beginning of chapter 6, we still have a general form, namely this type. This is general for any time variations, right? And then toward the end of chapter 6, then we begin to focus on what we call time harmonic. And then furthermore, in chapter 7, we assume source-free region. So these are the kind of equation they were to work with. In this case, these become complex function of space. These are complex. Whereas here, all of these are real function. The E and H, the B, these are all real functions. Does it make sense? All right. So that's basically chapter 6 for transformer problem or the motor problem or generator problem. This is how you end up. So we call this a VEMF, right? We give it a name. We call this VEMF, electromotive force, and we call this term, this whole thing, we call it the flux, right? The total flux. So this is called the displacement current. So these are the few terms that you need to understand. And if I give you a simple circuit that have capacitor, I could have asked you, I give you the material property, I can ask you how much current flowing through that capacitor. So I think we look in one of the quiz questions. Make sure you understand that quiz questions, right? So if the material between the two plates of the parallel plate conductor is perfectly dielectric, then you only have displacement current. However, if the material is have slightly some loss, in other words, the conductivity is not zero, then inside that capacitor, you will have both conduction current and also the displacement current, right? So how do you find for displacement current? First, you find the magnetic electric flux density.
Please?
I'm sorry?
Can you repeat that, what you just said?
Okay, so let me just draw this. Let me just draw this. Suppose I give you a circuit that look like this, right? I have some, oops, I have this too sensitive. I have, oops, no, let me do this. Let me use a different color. All right, so let's say we do this. We have a source. Of course, it has to be time varying now. And if I now put a plate, now I can put any material in between these two parallel plates, right? I can put any material. So suppose I have some kind of material here. Let me use a different color. Well, maybe just this green color here. So I put a material right here. Now this material, of course, these are conducting, perfect dielectric conductor on the plate. Right here is another perfect conductor. And maybe let me erase this so that it's not a short circuit. This is just, right? So I have a material in between them. So here's the material in between them, right? And if this material is characterized by mu, epsilon, and sigma. Now, if sigma is 0, which means this 0, what does it mean? It means it doesn't conduct any electricity, right? Or it is a perfect dielectric. In that case, this material is characterized by two parameters, mu and epsilon only. Now, if the mu is equal to mu 0, we say that that material is non-magnetic. If mu is not equal to 0, then it is has some magnetic property. So you can have paramagnetic or diamagnetic or ferromagnetic. All right. So those are the terminology. Epsilon, on the other hand, is basically a dielectric constant. So if sigma equal to 0, this material, if mu is equal to mu 0, then we say that material is pure dielectric, which means that there's no conduction current. So the current that can flow through here, if this is time varying, like in this case, is time varying, and there's a current flow, the current that can flow through there is what we call the displacement current. Now on the wire, the sigma, we assume the wire is a perfect conductor. Therefore, sigma is basically approaching infinity. Therefore, on the wire, electric field cannot exist. Therefore, on the wire or inside the wire, there won't be any displacement current because the E is equal to 0. Therefore, the D is also equal to 0. So the only current flowing through the wire is purely conduction current. Does it make sense? So then, because this is a circuit, a closed circuit, in this case, the conduction current must be equal to the displacement current. However, now, if my material here has some sigma, then there are two kinds of current that can flow through this material. One of them is the conduction current, the other one is the displacement current. Therefore, the conduction current flowing through the wire is equal to the sum of the conduction flowing through the material and the displacement current. Does that make sense? Any question about that? Oops. So this is V. Oops, let me use a different color. So this is VC, V whatever, just the voltage, right? Any questions?
Dr. Tawasha, could you repeat that last part again about the sum?
So here in this wire, you only have conduction current. Now, generally through here, you have two kinds of current. One is conduction current, let's call this prime because it's different from the other one, and then plus the displacement current, right? Let's call this prime. These are the current flowing through the medium between the plate of the capacitor, right? So, therefore, what is IC prime? IC prime is nothing but integrate over the surface or the area of the conducting plate of sigma times the field in between them, right? E dot with ds. Now, remember, these are all vector. You have to dot with ds, right? How about the I displacement? The ID is equal to the integration over the surface of, if there's no change, assuming that the structure doesn't change, so we can have this partial derivative with respect to these, and then it's epsilon E, right? Oops, I'm sorry. This should be not a phasor, but rather a time varying material, a time varying field. So partial this E, the whole thing, dot with ds. You see that? So now, if for sigma equal to 0, so let me use a different color. For sigma equal to 0, then IC prime is equal to 0, right? Any questions? So this one is the displacement current. This one is the conduction current to the material here. So now in this circuit, IC, which is through the wire, must be equal to IC prime plus ID prime. If there's no other losses, right? The KCL dictate that. Or in other words, if we apply for the conservation of charge. Then whatever charge I accumulate here, flowing through here must be equal to the charge flowing back, right? Because we don't create or destroy the charges. Any questions? So
No,
that's
that's good.
okay. That's part of the chapter 6. I think this also related to the quiz question that we had last week, I believe. So that's so chapter 6. The first part you look at is basically if I move. So let me. So another thing from chapter 6 is that you may have a simple thing is I may have I may have a rod, right? I may have a rod. Maybe here's a bar, and I move the bar. Maybe I move the bar at this velocity, right? And I have a field. For example, the field going. This is the electric field and magnetic field that I have here. So then the question is, what happened to the? So this is a conducting bar. It's a conducting bar, right? What happened when you do that? Well, you know that when you do that, there'll be a potential difference between. I can measure the voltage. Let me use a different color here. I can measure the voltage between here and here, right? So here and here, there'll be some voltage, right? So what is that voltage? You can calculate that, right? So this is basically the V. Maybe let me erase this. This is the VEMF that you have. We talk about, right? This is the nothing but the VEMF. So here what we have is the VEMF. So I have this EMF. So if I move this around, I think I showed the example both this way and also using a different way, solving it using the other equation, namely we solve it also using this idea over here in your notes. Show the derivation, right? So that's usually if I move a conducting bar in a magnetic field, it will generate some kind of voltage between the between the ends of the bar of the conducting bar. What is that voltage? Well, you can use something called the Faraday's law to figure it out, right? Any questions? So that's the first part of chapter 6 basically deal with the changing of flux. How does changing of flux produces VEMF? That's the first part of chapter 6. The second part of chapter 6 has something to do with this guy over here, displacement current. And then the other part of chapter 6 also talk about different kind of current. You have conduction current, you have displacement current. So conduction current has something to do with medium. And then the last part of the chapter 6 is the, of course, in chapter 6, we also talk about the idea of conservation of charges, right? The basically related to the KCL. And then we talk about the time harmonic. How do we represent a particular type of time variation using a simplified phasor notation in vector? Any question about that now? So make sure you know how to solve this and look at a lot of homework problem, example problem. Yeah, they're bound to be questions associated with this and questions associated with this. And then if I give you also give here, if I tell you the epsilon, mu, and sigma, if I give you the magnetic field, can you tell me the electric field and vice versa, right? How do you solve that? Suppose I tell you the medium, and I tell you inside that medium there's the electric field. How do you solve for the magnetic field and vice versa? So there are examples, samples in the book that tells you show you exactly how you solve that. So if I give you E, can you tell me what H is, or can you tell me what B is? Right? If I give you mu, epsilon, and sigma, if I tell you the electric field, can you tell me? Right? Once you solve for this, you can also solve for the other two. So if you know one component, can you solve for the other component? So why do you want to do that? Well, sometimes, for example, to solve for this, we need to use a flux. If I know the flux, B, I can also find the E, and vice versa. So chapter 6 involves how do you find different parts. One, because as we discussed, once the time variation in the source or in the field, the electric and magnetic field, they are related, they're coupled. What do you mean by that? What we mean is that if I know the electric field, I know the magnetic field, and vice versa. I can solve one from the other one. So how do you solve it? Well, you just apply the Maxwell equations. This is what you do. Now, there are several simplification, additional formula in chapter 7, for example. Now, unless you are comfortable with that, don't try to memorize this formula because this is the basic. This is what you need to know. So in a source-free region, we don't need to worry about this term, right? In a source-free region. And in the region where there's no loss, we don't have to worry about this term. So in that case, the relationship between the B and the E and the H with E and D are very straightforward. Okay, so it's just a simple derivatives. Any questions? So that's why this example in the book that talks about those kind of examples is just basically to reinforce the idea that once you have time varying case, when the electric field is changing with time, or the magnetic field is changing with time, or the current or the source is changing with time, uh, this electric and magnetic field, they are coupled. They are not independent anymore. They are not separate anymore. Now, if you look back to chapter 4 and chapter 5, uh, they are decoupled. They are, in other words, if I have a charge that doesn't change with time, doesn't move, it only produces electric field. I know nothing about magnetic field. And similarly, if I only have a current, DC current in the space that where I'm observing, the only thing I know is the magnetic field. There's no electric field. But as soon as you make changes, I mean the current or the space setup that change with time, the electric and magnetic field occur simultaneously, and they are related. So that's a key idea that is that you the gap, I'm not the gap, but the changes from 4-5, I mean, yeah, 4-5 to beyond 6 and 7. Now, if you want to tie everything together for the entire semester, 7 and later part of 6, 7 to some degree, chapter 6 to some degree, you can still see where the current flow. So you confine the current flow on a wire and so on, right? Now, once you go to chapter 7, you're now observing the property of electromagnetic field in open space, where you do not confine the current to flow on a wire anymore. So you need to vector to describe all the properties. But if you look back at the formulation, they are very similar to what you see, what you encounter in chapter 2, the transmission line. What's the difference? In transmission line, we do not have to worry about where is the electric field oriented, where is the magnetic field oriented, because it is dictated by or determined by your transmission line. So the electric field is perpendicular to the two transmission line, the conductor, and the magnetic field is basically confined within the two conductor. So you know where they are, and where does it go? Well, it's follow your transmission line. So for that kind of problem, we only have to worry about how far it is from the generator, how far it is from the load. Whereas now in chapter 7, uh, we don't know because it can be anywhere in space. So we have to describe the field in terms of where it is propagating, how does the electric field oriented, how does the magnetic field oriented. So the orientation of the electric field changes. We call it polarization. And then we have propagation directions. So as we discussed in class, there are infinite possible combination or what they call it, a type of electric field inside a room, inside a given region. So that's why in chapter 7, we focus only on the simplest possible form, namely the plane wave. So after you study chapter 6, this chapter 7 is basically a special case now. So basically, we are looking at um, a wave that is the simplest form in free space. So for example, we, in this case, since we know the variation is time harmonic. What do we mean by time harmonic? So in other words, my electric field now, let's pick a coordinate system. Let's assume it's function x, y, and z and time. So it becomes some function of, for example, it can be a function of space. Let me call this ER, right? Maybe a function of x, y, z, we don't know. And there's something called multiply with some cosine of some kind of time variation plus, so I may have kxx plus kyy plus kzz, right? Maybe like this. Maybe I should make it even more general. I may have some kind of phase shift plus phi e, right? Maybe it doesn't look nice. Maybe, well, I think that's fine. Let me see if I can do something about this. Maybe remove the whole thing. Move it here. So I can now, yeah. So this whole thing, basically, so the key thing here, the time variation. So the time variation here is a cosine omega t. Now this part, this part over here tells you the propagation directions, right? Inside the cosine function here. So this tells you the propagation directions. This is telling you the phase shift with respect to cosine omega t, right? This is the part that tells you about the polarization and how strong the field is. In other words, the orientation of the electric field. So this kind of field is called time harmonic because in terms of time variation is determined by cosine or sine omega t. If it is of this type, we can represent this whole thing using the complex form or time harmonic form, which is this, right? Which is the time harmonic form. Time harmonic, again, we assume that source-free and stationary and so on, we can represent using the complex form, which is function x, y, z only. And this is complex. This is equal to this real one, originally is real, x, y, z only. And then we have the e to the j phi e, right? Hopefully you still remember how we get to this point, right? Any question about that? So this is what we call the time harmonic form or complex phasor form, complex vector phasor form. So this is not the simplest one. Oh, there's one more term I forgot. Actually, there's one more term. I forgot one term. This part over here. So this part over here is basically, let me combine this. I have one more term which is multiplied with e to the j k x times x, e to the j ky times y, e to the j minus k. I should do, well, here I use plus. I can use c times z. So I should for positive propagation going, I can assume it is all minus here. Oops. Let me use a bigger one. Okay. Can I erase this anymore? That's weird. Well, anyway, so let me just cross this out. Negative. So to make it consistent. So it's so this is so I can rewrite this as e of r function x, y, z, which is a vector of the polarization. ej phi is the phase shift. And then this I can write the whole thing down as e times e to the minus j, the k vector dot with r vector. I can do it this way, right? So this k vector determine what is the direction of my wave propagation. Now, of course, the simplest kind, the simplest form, which we discussed in class, the plane wave, is only a function of, let's say, simplest form, let's say, x polarized and propagation in z directions, right? Suppose it's propagation in z direction, positive z directions, right? So what does it look like? In this case, the E is only function of z. It's propagating in z directions. And we have basically the polarization is x direction. So we have x hat, some constant E0, some value. And then we have e to the j. Well, sometimes we just say k times x minus. So that's, oh, sorry, k times z. K times z. So in this case, we assume the phase shift is 0. So this is the simplest form. This is the plane wave propagating, in this case, in the positive z directions and polarized in the x direction. So it's a linearly polarized plane wave. So what is this k? This k actually, so in this case, you can think this is equal to the kz over here, except for this case, the kx is equal to 0, the ky is equal to 0. Just so, um, um, well, probably in this case, for this, for the test that is coming up, if you understand just single variable, that's probably, you need to do that first before you get into the general case. So I think all the homework, except for a few that is slightly more complicated function, right? Homework, basically, this is z propagating. Of course, I can have both x and y direction and so on, but this is the simplest form you can think of. So this k has something to do with the propagation direction, and also has something to do with velocity, actually. So k is nothing but, in this case, k is equal to omega square root of mu epsilon, right? Or which is also equal to 2 pi over lambda. So either way, it's the same results. Any questions? So that's chapter 7. So basically in chapter 7, if you are given the expression like this, can you tell me what is the wavelength, what is the frequency, what is the polarization, what is the propagation directions? And then from here, can you solve for the magnetic field intensity? Once you do the magnetic field intensity, can you tell me the time average power of the wave? So that's pretty much the key concept that you need to understand from chapter 7. So what kind of question I can ask? So for example, I'll give you some expression that look like this, with some numbers, and can tell me what is the frequency, what is the polarization, what is the amplitude of the field at a given position and at a given time, right? And what is the propagation directions? What is the wavelength? What is the speed, the phase velocity of the wave? So these are the few um, parameters that I could ask you to determine for a given expression. Or on the other hand, the reverse is true. I can give you the frequency. I can tell you, okay, I have a plane wave, uniform, propagating in the y directions, and polarized in the z direction, and at the position y equal to 0 is, because it's propagating in y direction, position y equal to 0, the amplitude is 10 volt per meter, for example. All right. So can you write down the expression, the equation in time domain like this, or in the time harmonic complex domain like this? Can you write down the expression that describe the field? So that's a very basic that I would expect you to be able to do from 7. So the key thing is that you know what plane wave is, what is its behavior. Now, can you put it down on a piece of paper describing it mathematically, and then allow you to do some analysis. And of course, to determine the power density, you just do the time average power density is 1/2 real part of E cross H conjugate, right? So that's pretty much fixed. We didn't have a chance to derive that equation, but that's pretty standard equation. So I'm not too worried about that part in terms of derivation, but you should be able to understand what those formulation means. Any questions? Any question at all? So let's take yeah, go ahead. Yes.
Yeah.
Go ahead.
One person speak at a time, please.
Could you go over that time average power again? I'm sorry.
Okay, time average power. Let's take a look at this one, right? Let's take a look at this particular example right here. Right. Suppose I give you this. Suppose you are given at one more page. Suppose you are given time harmonic form. So I give you this, right? And all right, when you see this, what comes to mind immediately? Well, this electric field is a function of z. So it changes with z. Therefore, just by looking at this, you know that it's going to be propagating in the z direction, right? It doesn't change in any other direction. So it should be, in this case, it should be a plane wave. So now if I give you more, for example, with this, well, this then is polarized in the y directions. Maybe I just put 10, right? So the amplitude is 10 throughout the xy plane, but all the electric field variation or fluctuation in these y directions. Okay. So if I ask you what kind of antenna that can produce this, well, the antenna, suppose you say dipole, suppose my dipole is infinitely long. The dipole is oriented toward the y directions, right? And then we have e to the minus j k z. So of course, k I can tell you, if I tell you the frequency permeability and permittivity and assume it's lossless, then K is fixed. K is equal to omega mu epsilon. So suppose this is, all right, so well, yeah, instead of putting 10, let me use just generic. All right, so generic here. So let's call this E0, right? So it's generic constant, right? So how do we solve for the H? How do we, so determine, so this is an example, also homework problem. Determine H, see? Also determine E, function of Z and time. I can also ask you what is H, function of Z and time. What is the power density, average power density, which is this average power density, right? Time average power density. So how do we solve that? Well, how do we find H? Well, we know that curl of E for time harmonic, function of Z equal to, what do we have? Negative omega mu H, right? Therefore, I can solve for H of Z equal to 1 over this, right? 1 over minus J omega mu. These are all given. I give you omega, I give you mu, and I have to do curl of E as a function of Z, right? So how do I solve for the curl? Well, in the rectangular coordinate system, what is curl? Curl is, oops, let me just expand this. So in the rectangular coordinate system, this term is constant. This is constant. So if you know mu value, you know omega, this is constant. This 1 over negative J is simply J, right? So if this is just a constant. So what I'm going to do is I'm going to put this, let me erase this. Right. So this equal to 1 over minus J omega mu. Of course, make sure you still remember how to do complex numbers. And this is nothing but the curl operation in rectangular coordinate is very simple. I have x hat, y hat. Oh, by the way, this is calculus 3. And then inside I have partial derivative, right, with respect to x, partial derivative with respect to y, partial derivative with respect to z. And E, I only have what component? I only have y component here, y hat component. So I have 0 here. Y hat component, I have E0, e to the minus j kz, and I have 0 here. So I have to solve for the determinant. So how do I solve that? Well, this one, remember these are determinant. So this one is this and this, right? So I have, let me clean this up. Okay, so I have now this equal to, let me put it here, maybe let me put it to the side. Is equal to 1 over minus j omega mu. So I have basically, let me put this x hat negative, right? This one go with this one and minus this, right? So minus, so partial derivative of this. So let me just write the whole thing down. So I have partial derivative with respect to z, E0 e to the minus j kz, right? So that's the only term I have. And then what else? Oops. Then I have, how about the y hat? The y hat, well, is this and 0, nothing, this and 0, nothing. So I don't have y hat component. How about z hat? Well, z hat I have something. I have z hat, I have this with respect to x was 0, and I have this, right? Partial derivative. This is not function of x, so it's gone. So I only have this term actually. And any question at all? So what do I have now? So I have, what is this? This is nothing but minus minus. I have j, k, and then E0, e to the minus jkz, right? And the whole thing I have here, let me erase this one. Whole thing I have here now is is equal to J, negative J, cancel out. So I have negative 1 over, oops, negative 1 over omega mu. I have K, I have X hat, K E0 e to the minus J kz. Now K over omega mu, what is K over K is, so I have, oops. So I have, let me go up a little bit. So I have X hat, K is omega, so it's negative. So negative, so it's negative X hat. K is equal to omega square mu epsilon over omega mu. So omega and omega cancel out. And then I have E0 e to the minus J kz. Then it gives me minus X hat. This is nothing but square root of epsilon over mu E0 e to the minus J kz. So that will be my H field. So what it says that my H field is also polarized in the Y direction, except it's negative, right? I'm sorry, in the X direction, the polarization. And the amplitude, this amplitude of my is a constant. Epsilon is a constant, mu is epsilon, E0 is a constant. So I can call this H0. So the amplitude is H0. And what is the propagation direction? The propagation direction is in positive Z directions, right? Given by here. And so this is H of Z correspond to the E of Z that we had earlier. So something interesting here, we have a constant here. And the constant, actually I can write down this whole thing, H0 is actually equal to, I can write down it's equal to E0 divided by square root of mu over epsilon. I just move it a little bit, right? And now this square root of mu over epsilon is interesting. It's called the intrinsic impedance of the medium. So actually it's equal to epsilon 0, something we call this eta. It's a constant. So for a given medium, this eta, which we call intrinsic impedance. And the unit for this intrinsic impedance is ohms. But anyway, for plane wave, this is some interesting property. In other words, once you solve that, the ratio of the magnetic field to the electric field is actually a constant for plane wave. And that constant is this eta, and it's determined purely by the property of the medium. In this case, we assume that the medium is lossless. So that's how you got the H, right? Any question? Do you see all the steps? Now, what's usually what people have difficulties? Not this. Do you know the idea? What the problem people have is, well, how do I do this curl right here? They forgot about this. So that's the problem. They forget about a complex derivation. Complex division, another problem, right? And then just doing simple derivative from your 2347. So that's another issue that some people have. So it is basically figuring it out. The idea is very simple. You know this already. This is Maxwell equations. How do you get if you're given this? How do you get all the way to solve for the field itself, right? Oops. Oh, I messed it up. Yeah. So basically, how do you solve for all the way to this field? So the H is basically this. This is the H. Any questions?
Dr. Twaja?
Yeah.
There's another simpler formula that it's from the book, and we can calculate, for example, electric field from H using just the intrinsic impedance.
Yes, if you know it's a plane wave, yeah. But this only gives you the amplitude, right?
Oh, okay.
So if you know all the tricks, let me put it this way. If you know the property very well, then you don't have to go through these formulations, right? You can actually, by inspection, you can just find out exactly what, if I know the H, I know exactly what the E is. And that you have to be very careful with that in chapter 7 and chapter 8. They give you a lot of these special equations. The best way, since you guys are still learning this, the best way is just stick to the basic. It doesn't take much time to go through these steps, but at least you know what you're going. You don't make silly mistakes. Yes, indeed. If you know, for example, here, the E field, right? What happened to the E field? The E field, right? The E field is polarized in what direction? So the E field is Y hat, right? The E field, oops. The E field polarized in Y, the H field is polarized in negative X. All right, and the propagation direction is in Z direction. So
Z direction.
these are related. These are all related. So, but if you remember this, then of course you can do this, but don't try to memorize this. I will not, unless you already have been using this for some time and it's become you're already comfortable with this. So that's the challenge with chapter 7 is that as the author goes along, it starts throwing you a bunch of special equations. Oh, H is related by this K 1 over eta stuff. Those are coming from here. If you remember this, this is good enough. You can derive anything you want, and you won't make mistake if you know how to do this. So I can give you any kind of polarization, any, you can always do this.
Yes, sir. Thank you so much.
Oops. So the question is that, am I going to ask question about using cylindrical coordinate system, spherical coordinate system? The answer, of course, is yes, if I want to torture you, but it doesn't make any sense, right? If you don't understand the rectangular, why would I ask you to do the spherical coordinate? It's just tedious mathematically. Conceptually, there's nothing special about it. Does it make sense? So make sure you understand the very basic idea first before you attempt to try to do shortcut. All right, so we've managed to take care of the first part. How do we find this e to the z as function of time? Well, to do this, you need to remember the convention that we use for electrical engineer, right? To get from this E to this E, how do we do that? So let me use a different color here. So I can, to get to determine this, then we have E, ZT basically is equal to the real part. This is critical. We have E, Z times e to the j omega t. So we just have to do that. And then recognizing that e to the j omega t is cosine omega t plus j sine omega t, we multiply them, take the real part, and that will be the answer for that. Okay, let me, instead of solving it, do you guys know, who doesn't know how to take care of this part? I think the book has some example and also some sample how to solve this. Make sure you know how to do this. And the key thing here is this. For electrical engineering, we use e j omega t. Again, if you go to science, you go to physics, you go to chemistry, they are most likely using e to the minus j omega t. So all the formulation that they develop in those books or in those report, if somehow the result is kind of conjugate of what we have. So in this case, e to the minus jkg for us is going in the positive z directions. If I use a different convention, it will be e to the plus jkz is going the positive. So that's somehow confusing. So once you understand about this convention, then you stick with it, then you're fine. Otherwise, what is the meaning of this? You don't know. So what if you don't really know? Well, you go back to the time domain and you should be able to see it, right? Everybody see this? Do you know how to determine this one? Same way. You just apply here, you multiply this thing with the e j omega t and then take the real part. And then you get the HCT. All right? Any questions? Any question up to this point? So that allow you, remember these are mathematical representation. We represent in complex domain. Why do we do this? Because it's simpler and easier to analyze and describe. And we don't have to also to solve because we don't have to worry about time dependency. We only have to deal with three-dimensional. It's a four-dimensional. This is exactly the same thing that what you did in your circuits too, or in circuits where you have time varying signal. You go into phasor, in which case you just have to solve for a complex number as opposed to a time functions. Right? So exact same idea, except now our phasor is a vector phasor rather than a scalar phasor that you are dealing with in circuit 2 or circuit toward the end of circuit 1, because in circuits, all of your current and you assume that the field is negligible, but your current, your voltage are confined in your circuit, so you don't have to worry about location and position and so on. So you only have to worry about the voltages at given locations at different point in the circuit, right? So how do we determine the time average power of the signal? This is called a time average power. So this is basically given by, the time average power is given by, so let me use a different color. Let me use this red one. So this guy over here, this is given by, we didn't have a chance to derive this. It's nothing but 1/2, take the real part off, let me make it smaller. Hold on, let me just make it smaller. This is way too big. So how do we solve this? So this, the time average, of course, this is a vector. So sometimes we just put average over here is equal to, so because it's time average, it's no longer a function of time. It is a vector. Vector tells you where it is going. So this is basically 1/2 the real part of E. This is the vector with cross with H conjugate. So what is H conjugate over here? H conjugate, well, this is the only one that's complex, right? The conjugate becomes e to the jkz, right? So E, I know you have y hat. This is minus x hat, so you have the cross product. So how do you do the cross product? Well, to do the cross products, again, you do the vector notation, right? So this one for here is basically we have x hat, y hat, z hat. Hopefully you still remember this. So if E have all the components, so I have EX, EY component, EZ component, right? And I have HX, HY, HZ component. And then I took the determinant. So in this particular example, the E only have Y component, so only this exists. This is 0, this is 0, right? And how about the H? H only have X component, this is 0, this is 0. Therefore, you do the cross product, you end up with this. Take the real part. Of course, you have to do conjugate. So conjugate means this is a plus, so you do the conjugate. So let me put down here. So this should be conjugate, 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 right? Right? So after you do the cross product, then of course you take the real part out of it, you multiply 1/2, that will give you your time average power density. So this is the amount of power per unit area in that particular location, location in Z, right? You average over time. So it tells you this, tells you where is the power going or being delivered. Of course, for plane wave, the power is delivered in the same direction of where the wave is propagating. So that's a typical question for chapter 7 type. In other words, do you understand what do we mean by plane wave? The property of plane wave. So the property of plane wave include what is the frequency of the plane wave, what is the wavelength of the plane wave, what is the phase velocity of the plane wave, right? And then if I give you the electric field, can you solve for the magnetic field and vice versa? And then can you tell me where is the power flow? That's about it. And then if I give you one, can you solve for the other one? You know, if you know the magnetic field, can you solve for the electric field and vice versa? So basically, a key thing is understanding the property of plane wave and how different components link. And as you know, as we discussed yesterday, the velocity, the phase velocity of the wave is determined purely by the medium, which has something to do with 1/square of mu epsilon. So you can derive different kind of parameters from those formulations. Any questions for in terms of preparation for tomorrow's exam?
So, Dr. Tawasha, there won't be anything from chapter 8?
At this point, I don't plan to putting anything on from chapter 8 because make sure I understand this part first. Yeah, chapter 8 is more with reflections. So I may throw in as a bonus for the final exam, who knows? But it is basically, if it's normal incident, if you read ahead, normal incident, the formulation is exactly the same. Well, actually, it's very similar, or it should be similar to the reflection coefficient that you guys learn in transmission line, because in transmission line, the wave, when it hit the load, it is normal to the load. Now, in chapters 8, the wave can have all kinds of orientation, right? all kinds of direction relative to the boundary. So then you have reflection coefficient, the Snell's law, but we didn't have a chance to go through that, so I'm not going to ask question in the for the test.
All right, thank you.
All right. Any other questions?
So if we understood Afshin's quiz, we should be pretty confident in our abilities on the test.
Which questions?
The quiz that Afshin gave us. It was like
Oh, I mean the TA gave you.
yeah,
Well,
yeah.
he tried to encourage you guys to study ahead because he was brainstorming, trying to figure out what can motivate you guys to really come to the review session and so on. So that's why he thought that maybe give some partial credit and make people come in and hopefully this will give you the things that once you spend time you learn more. So he was really also concerned when he saw the result and he wants to help you guys. So yeah, I think it will help. I don't know how much help. Again, as I mentioned earlier, a lot of times um, you will get stuck not because of the concept, but rather you don't know how to do the curve, right? Or you forget how to do the curve. So a lot of time, this is they forget how to get from here to here, for example. Then you're stuck, right? So to a short answer to your question about abstinence, I cannot guarantee that the question he asked will be the same type, but if you understand the concept, that should help. I don't even know what kind of question he asked you guys. So he tried to kind of extract it from the homework assignment, if I'm not mistaken.
Yeah, it was a plain way from the homework. Yeah. All right. Thank you. Thank you.
Right? Any other questions? So again, don't try to memorize the formula, but rather step back and see how those formulas in the chapters are related to each other.
Dr. Tuwashan,
Yeah.
tomorrow's going to be the last day before the final. When can we expect? What can we expect on the final itself?
Well, for yeah. Well, the final basically to start with, how are you going to study those? First thing is I review all the tests, right? You'll be basically covered. See, the test basically tell you the answer. Someone have a real bad feedback between the microphone and the speaker. Yeah. So if I were you, I will probably study the all the test questions, all the quizzes, and that kind of usually give you um, an idea of what are the important concepts that you need to know. And then you go back and look at the relevant concept in those chapters. So that is what I would recommend. It will not cover any new material in the so it meant to be a final review. That's why the idea is that you can drop the test so that at the end you have a chance to show that you actually know the stuff that you previously missed.
All right, thank you. Dr. Chacha, can you talk about the impressed current?
Okay.
Like why when it's time harmonic and source free, why is it zero again?
Now, for example, in the beginning of chapter 6, we talk about we put a current. Now, in this case, let me see. Let's see. Right here. So you can think of this current. Okay, this is the current we put in from the source. So this is nothing but these are the current we impress, we put in. Does it make sense? Or we can have or in the transformer question that we had before. So in the transformer, you put a current, right? In the transformer, you have a wire and you have something called impressed current. You put it in. So in that kind of problem, for the transformer case,
hey guys, welcome back.
Produce this is what you put the current to produce a magnetic field. That's what we call impressed current. The current that you put in. Does it make sense? So you may have a loop, right? You may have a loop that you put a current in. That's your impressed current. That current produces the field. Now in the source-free region, you don't have impressed current anymore, right? Because the field is due to the source outside of the area, outside of the region. Does that answer your question?
Yes. So like if we have a source, will put it in a impressed current. So how is different from the conduct current? So
No, the conduction current is this. Let me do this, right? Let me. So suppose now I have very simple. I have a loop, right? So I have maybe a very simple loop, right? So So I've connected this to a source, assuming that this doesn't look good at all. So let me, so suppose now I have a loop that look like this, all right? So I connect this a source that's tiny, small compared to my circuit, right? The source is small, and the current, let's say, flowing like this. So this is my impressed current. I put in here, right, in the space. Okay, this is some time varying. So my current may the current may be, let me make it nicer. So this is my impressed current. If I want it to be correctly, actually it's a vector, right? Suppose I do my coordinate system. Let's say this is over here is z. So of course this is not my phi. So my IE is a phi hat directions, some kind of constant current, function of time I0, and a cosine omega t, for example, right? So this will be my impressed current. This current will produce magnetic field, right? You produce the field. So let me use a different color. This current then produces field that is maybe red. So it's going, the current is flowing like this. So what happened to the field? The field is a right-hand rule. So I have field that is going out from the inside, right? Correct. And then going in on the outside of the loop, right? So everywhere outside the loop, the field is like this, right? Does that make sense? And this field, of course, produces also electric field. So you have electric and magnetic field both outside here. So I have both E and H outside here, right? And if the medium, let me use a different color now. If the medium outside or inside, doesn't matter, is characterized by mu, epsilon, and sigma, there'll be some current flowing somewhere here. So there'll be some conduction current flowing in the medium, and it will generate heat, so it's losses, right? So the current is due to this sigma. These are conduction current. Okay, so the impressed current is the current that you put in. You purposely put in, and this current will generate the magnetic, in this case, magnetic field. The magnetic field in turn, because it's time, is vary with time, right? In turn also produce electric field, and the two of them are related. And then if the medium here have conductivity, then there's inside the medium, there's some kind of current flow. That current flow is the one that consumes the energy or turn into heat. Does it make sense? So now if I want to describe the equation for the entire region, then I have to use the equation that include the impressed current. However, if I'm only interested in this particular region over here, for example, then the impressed current is 0 in this region. In this region, I only have the conduction current. However, if my sigma is equal to 0 right here, then there's no conduction current. Only impressed current. The whole thing has impression amount. In this region, there's no conduction current at all. You only have E and H field. You only have E and H in here. Any questions? Does that answer your question?
Yes, thank you, doctor.
Anybody else?
Dr. Chuacha?
Yeah?
So will chapter 8 be included on the final exam?
No. As I mentioned earlier, if I decide to add, I'll probably add a bonus point or something like that. If for your effort, if you know.
Okay.
Yeah, but definitely you should be able to get 100 point out of whatever we cover up to chapter 7. Any other questions?
So our best resources for setting the final will be the previous quizzes and exams.
That's I would start with those, and then you after you start with those, then you go back and look at chapter 2, 3, 4, 5. Basically think of, suppose you were to teach the class, right?